So by now you should have already known that wave can be represented sinusoidally. Um, Sine waves look something like this. Sine graph looks something like this. And the equation which we use to represent that is y is equals to a sine wt. This thing is omega. I think that's the actual name of the symbol, but whatever, I'll be calling it w. So this single equation is what's going to lead us to all the other equations which you need to know. So you don't need to cram really. Now if you did circular motion, by now you should know that this omega angular frequency, right, is equals to 2 pi f, right? So we substitute omega into this equation. This is sinusoidal wave equation. So y is equals to a sine 2 pi f t. Already got our second equation. Now to get our third equation, we need to expand further. Now in a wave, there might be a lead or a lag. There might be a lead or a lag, and that's what we call what phase difference. So we see this time quantity right here. This is what we're going to segregate into to account for a lead or lag in time. So how I'm going to do this is I'm going to use the formula for velocity. So we know velocity is equals to distance. I'll call it the distance x over time, because if we're drawing the normal wave diagram, it's going to have a what? A y-axis and what? An x-axis. So that's what we're going to use for our formula for velocity, distance over time. Now we make time subject of the formula. So if we make time subject of formula, you have what? X over v. So we're going to segregate this time here and account for a lead or a lag, and that's what exactly what I'm going to do. So we have a new equation, y is equals to a sine 2 pi f in brackets. So I'm going to break it into what? Time minus what? Minus time. This is also time, right? So we can say minus x all over v. It does not change the homogeneity of this equation. It's still going to be the same unit. It's consistent. That's what that means. Okay, so how can we simplify further? We can then open these brackets and multiply through. We're going to get another equation. So I'm just going to call this equation 3. Let's get another equation. To get another equation, I'm going to say y is equals to a sine 2 pi f t, right? I've opened the equation. Let me put this in brackets. 2 pi f t minus 2 pi x over v. There's also times f here, right? Because we open the bracket with 2 pi f. So if we simplify this further, I'm going to get y is equals to a sine. Now remember, f over v is what? Or v over f is what? Lambda. Remember this formula, v is equals to f lambda. Therefore, we can say lambda is equals to v over f. And if lambda is equals to v over f, it just means that 1 over lambda is equals to f over v, right? So f over v is 1 over lambda. And I can replace this f over v here with 1 over lambda. So we have an equation 2 pi f t minus what? 2 pi x times 1 over lambda is going to give us what? Over lambda. So this is one of the main equations which we are going to be using. I can just call this number 5, call this number 4. It looks like there are a lot of equations, but it's basically the same sinusoidal equation. So in JAMB, you'll be given a wave equation. All we have to do is what? Is compare the one that resembles the equation and what's used to get our unknown quantity. So for example, you are given a wave equation that looks like this in JAMB. So 50 sine, let's say 50 sine, probably 50, let me just use a random figure, 20 ft, sorry, 20t probably, and they say you should find the parameters. Obviously a is amplitude, so our amplitude is going to be what, 50 meters if they say y is in meters, right? Then they say you should find frequency from this equation. We can just say 2 pi f is going to be equals to what, 20. Therefore our frequency is going to be equals to what, 20 over 2 pi. You can use 3.14 as the value of pi and you get to what, the frequency in hertz. So that's just what mathematical wave equation is all about.